Hi there, folks. Today we're looking at dividing rational expressions, and really dividing rational expressions comes down to this thing called rationalizing the denominator. The idea is that we don't want radicals in the denominator, whether it's a square root or a cube root or a fourth root or fifth root. We don't want that in the bottom of a fraction. Okay, the numerator, that's fine. We can have radicals in the numerator all we want, but we don't want to have any radicals in the denominator. All right. And so when we're dividing rational expressions, essentially our goal is to eliminate all radicals from the denominator. All right. So when dividing radical terms, we want to rationalize the denominator. And again, rationalize the denominator simply means eliminating all the radical terms from the denominator. Okay. And really, this is kind of like getting common denominators when we really get into this. We are essentially looking at this and saying, I have a denominator that I don't want. I would prefer to have this denominator. How do I get that? Okay, like if you had a fraction of 1/2, you would prefer a denominator of 4, so you multiply by 2 over 2. It's going to be that same kind of concept, but instead of trying to get a specific number, we're just trying to get something that doesn't have a radical. Okay, the first thing you always want to do, though, is you want to simplify this thing just as it's written first to see if maybe the denominator rationalizes itself. Okay, always simplify the radical before you start to force rationalize this thing, okay? Before you start multiplying by anything or doing any of that kind of stuff, just simply simplify first to see what you're actually dealing with. And that'll have two effects. One, we might actually get rid of the radical in the denominator just by simplifying. But two, it might make rationalize the denominator and what we have to multiply by a little bit easier and a little bit smaller, okay? So always simplify first. For example, if I look at this guy, just like our rules for multiplication, remember multiplication and division are technically the same thing, so we can apply the same rules. Remember with multiplying, it was outside times outside, inside times inside. So with division, it's the same kind of thing. Outside divided by outside, inside divided by inside. So the numbers on the outside here are just ones. Okay, so it's just 1 divided by 1, which is 1 on the outside. But now I can divide the things that are inside the radical. I could say, hey, 63 divided by 7 is a 9. And again, that stays on the inside of this thing. X to the 5th divided by x to the 1st. Remember, there's a little 1 here. If you've forgotten that, remember when we divide, we subtract the exponents. And then here, y to the 7th divided by y to the 3rd is y to the 4th. Okay? And so what happens is, I don't even have a denominator anymore. Because I simplified a little bit, the denominator went away. Now I could start taking the square root. The square root of 9 is a 3. The square root of x to the 4th is x to the 2nd. The square root of y to the 4th is y to the 2nd. There's nothing left under the radical. So this one is rationalized just by simplifying. The denominator went away completely, okay? And there were no radicals left in the denominator. So always try to simplify first, okay? If I look at the next one, this is the same situation, except instead of having it written as 2 square roots, it's written as the fraction under 1 square root. That means the same thing. So I can start by just doing some division and simplifying this guy a little bit. Let me write it over here first. So if I do this, 8 over 32 reduces to a 1 over 4. And then that's going to be an x to the 6th. Again, if you forgot, we're subtracting the exponents. And then y to the 3rd. And now I continue to take the square root. And really, I just take the square root of numerator and denominator individually. So if I take the square root of x to the 6th, that's an x to the 3rd. If I take the square root of y to the 3rd, that's a y to the 1st with 1 left over. And then the denominator, again, I just take these separately. The square root of 4 is a 2. And that's it. And so even though I still have a radical here after simplifying, I don't have a radical in the denominator. Okay? And if you need to see this broken down, I'm just doing the square root of the numerator over the square root of the denominator. When I take the square root of a whole fraction, I just take the square root of each of those individually. Okay? And as I simplified, what happened is I no longer have a radical in the denominator, and that's the goal. It's okay that there's a radical in the numerator, but I don't want a radical in the denominator. Okay? If I look at this one, there's nothing that I can simplify here. I might try to simplify first, but in this one, there's nothing that I can do. Okay? I can't simplify this in any way, shape, or form, so what I want to do now is rationalize the denominator. I essentially want to use the same techniques for getting common denominators. I don't want a denominator of the square root of 5. I want a denominator that's anything other than a square root of something. Okay? And so really I just have to ask myself, what do I need to multiply this guy by? You know, when I dealt with fractions before, like, 1 over 2, and I wanted a denominator of 4, I would look at that 2 and say, okay, how can I turn that into what I want it to be? How can I turn that 2 into a 4? And I do that by multiplying by 2 over 2, okay? And so I asked myself the same kind of question here. What can I turn that square root of 5 into? And how do I turn it into that thing, okay? And so when you think about it, the square root would go away if I had a perfect square underneath there. Instead of a 5, if that thing was like a 4, then I could take the square root of 4 and get a 2. If that thing was a 9, I could take the square root of 9 and get a 3, okay? And so a 4 and a 9, well, that's not going to be easy. It's not easy to turn a 5 into a 4. It's not easy to turn a 5 into a 9. So think about a perfect square that's easy to turn that 5 into, and hopefully you come up with an answer of 25. I can turn that 5 into 25, so I want to multiply that 5 by 5. But here's the mistake students make. So don't write this down. But they go like this. They say, let me multiply by 5 over 5. Well, think about your rules here. This denominator would become 5 square root of 5. See, it's outside times outside, inside times inside. I want to multiply that inside number by 5. So what I really need to multiply by is the square root of 5. Okay? And there's kind of two ways to think of that. You could think of it as saying, hey, I want to get a perfect square under the radical, so I need to do inside times inside. Or you can think of it this way. When you think about a square root, it's the opposite of squaring something. And squaring something is really multiplying it by itself. So if I take the square root of 5 times itself, I'm squaring the thing. I'm undoing the process of the square root, which is what causes it to cancel. So watch this. If I multiply this out, that's going to be 2 root 5, outside times outside, inside times inside, over, here inside times inside is the square root of 25. And now I continue to simplify. The square root of 25 is just a 5. And now the denominator has been rationalized. And the 2 over root 5, that is equivalent, if we were to plug that into the calculator, as that would be equivalent to the 2 root 5 over 5, okay? But the difference is I no longer have a radical in the denominator, okay? And I can't simplify those 5s because one's on the inside and one's on the outside. Remember, applying that same rule that we had for multiplication, outside divided by outside, inside divided by inside, that's the answer for this one. We've rationalized the denominator, okay? This one is the same kind of thing. Again, you could break this up and say, hey, that's like the square root of 10 over the square root of 3. That means the same thing. When you have the square root of a whole fraction, it's the square root of each piece individually, okay? And so now from here, if I want to turn that 3 into a perfect square, the easiest perfect square to turn it into is a 9. So I'm going to multiply by square root of 3 over the square root of 3. And it's that idea of we still have to do the same thing to the numerator and denominator, okay? And so what I end up with here, I end up with the square root of 30 over the square root of 9, which is the square root of 30 over 3. And once again, I cannot divide the 30 and the 3 because one of them is inside a radical and one is outside a radical, okay? We have to keep those things separated, okay? And that's it. The denominator is rationalized. And mathematically, the what I started with and what I ended with are equivalent if I plug them into the calculator, but one has a radical in the denominator and the other one doesn't. Okay? If I look at something like this guy, these become a little bit tricky. And if you look at some of the examples that we've done in the past, it should give you some hints about what to multiply by. Students will try all kinds of things here. They'll try multiplying that 6 plus root 2 by itself, 6 plus root 2, but that doesn't work. They'll try multiplying by just the square root of 2, but that doesn't work. Okay? When we have a binomial down here, if you think about some of the binomials we've multiplied, the ones where all of the radicals went away were when we multiplied by the conjugate. So here I want to multiply by 6 minus root 2. All right? And again, whatever I do to the denominator, I also have to do to the numerator. All right? And it's just this kind of special scenario that happens that when I multiply by conjugates, the middle terms always cancel. And then the outside terms are something times itself. It's something squared, okay? And so this is the effect that happens. If I multiply out this numerator, again, it's our distributive property. I'm going to distribute the 2, which gives me a 12 minus 2 root 2. And then I'm going to distribute the negative 4 root 2. That gives me a minus 24 root 2. Plus 4 root 4. And I'm going to do the same thing in the denominator. I'm going to distribute. So let me distribute the 6. I'm just doing this in little pieces. So that's a 36 minus 6 root 2. And now I'm going to distribute the root 2, which gives me a plus 6 root 2 and a minus square root of 4. And so once again, when you look at that denominator, you see that the middle terms are opposites, so they're going to cancel out, the negative 6 root 2 and the positive 6 root 2. But the other big thing is, when I multiplied the 6 times the 6, it gave me a 36. I'm essentially multiplying something by itself. When I multiplied the root 2 by the root 2, I'm essentially multiplying that thing by itself, which gives me the square root of 4, which is going to end up being a 2. I'm canceling out the square root because things are getting squared, okay? And then the only place that I would be left with the square root is those middle terms. But the conjugates are special because the middle terms cancel out. And that's why this kind of works, okay? And so if I continue to simplify here, ready? This is 12. I can combine these middle two terms, the negative 2 root 2 and the negative 24 root 2 as a negative 26 root 2. Remember, those are like radical terms. Over here, the square root of 4 is a 2, so that becomes an 8 for this last term. Again, the 2 comes out, and we do a little more multiplying. Down here, that's a 36. The middle terms go away. The negative 6 root 2 and the plus 6 root 2 cancel out. And then the minus root 4, well, the square root of 4 is a 2, so minus 2. And now, once again, I can continue to simplify. I have more like terms here. That's a 20 in the numerator, minus 26 root 2. And now in the denominator, that's a 34. And so what I've done here is I've accomplished the goal of rationalizing the denominator, but I can actually simplify this a little bit now. Because all those things are divisible by 2, I can use my distributive property and say, hey, that's 10 minus 13 root 2 over 17. And now it's done. All right? And if you're looking at that thinking, well, that's not really any simpler than the original. Well, you might be right about that, but this is the simplified version, okay? According to the rule of rationalizing the denominator, okay? If I look at the next one, same kind of thing. I want to rationalize the denominator. Well, I just have to multiply by the conjugate. The conjugate creates the special situation that gets rid of all the radicals. So right here, instead of root 5 minus root 3, I'm going to do root 5 plus root 3. And whatever I do to the denominator, I have to do to the numerator. Okay? And so once again, it's my distributive property in the numerator. Again, and if you want to surround these with parentheses to help keep yourself straight, if you need to take it off to the side and draw your claw, okay, or show foil, all right, and then come back over here, that's fine. All right? But let's go ahead and distribute. If I distribute the 6, that's going to give me a 6 root 5 plus 6 root 3. And now also in the numerator, I'm going to distribute the root 5. That gives me plus the square root of 25, inside times inside, plus the square root of 15. In the denominator, I'm going to distribute the square root of 5, so that's going to be the square root of 25, plus the square root of 15. And now I distribute the negative root 3, that's going to give me a minus square root of 15, minus the square root of 9. And now I just continue to simplify. I look for perfect squares and that kind of thing. So in the numerator, the square root of 25 is a 5, so I can rewrite that guy as a 5. 15 I can't do anything with. So just keep going. In the denominator, the square root of 25 is a 5. The square root of 15 minus the square root of 15, those middle terms cancel out, so they're going to go away. And if you want me to show you, I could just cross those out. The square root of 9 is a 3, so that's minus 3. And now once again, I can continue to simplify by combining like terms. There's not much to do because the numerator, there's not really anything that I can combine. In the denominator, I have 5 minus 3, which is 2. And so now once again, I've accomplished the goal of getting a denominator that no longer has a radical. And yeah, if you're looking at this going, that's not simpler, Mr. Jansen. Well, too bad. If I say simplify, this is the simplified version, if you want to put that in quotes. Okay? Sometimes rationalizing the denominator does not make the problem look simpler, but we still consider that the simplified form, all right, because it's written the way it's supposed to be written. Okay? If I look at this guy, again, once again, I want to multiply by the conjugate. And we're doing a couple more of these examples only because these are the ones that students struggle with. Okay? So the conjugate here would be 1 minus root 3. And again, it's all about the denominator. Nobody cares about the numerator. We just do to the numerator whatever we do to the denominator, all right? It's just kind of tagging along for the ride, and it's going with the flow, all right? So now, once again, in the numerator, I'm just going to distribute that 4. And again, surround these with parentheses if that helps. Take it off to the side if that helps. So that's a 4 minus 4 root 3. In the denominator, that's going to, when I multiply this out, that's going to be a 1 minus root 3 plus root 3, and then minus the square root of 9. And here's the thing, if you remember that multiplying conjugates always get the middle term to cancel, and the reason I'm throwing these easier examples here, we can do a little bit of a shortcut. You could just say, hey, I'm going to do the 1 times the 1, and I'm going to do the root 3 times the root 3. That's going to be a minus root 9. Notice I just skipped those middle terms, okay? And it's because I can take a shortcut when I have conjugates because I know the middle terms are going to cancel, okay? And so I shorten this thing up a little bit for myself. And now I can say, hey, that's 4 minus 4 root 3 over 1 minus 3, which is going to be a negative 2. But now continue to simplify. I can use my distributive property here. That's a negative 2 plus 2 root 3. That's it, okay? Next one, same kind of thing. Let's try the shortcut here. But again, I want to multiply by the conjugate. Again, it's all about getting rid of the radicals from the denominator. So that's how I choose the conjugate. It's 5 plus root 2. And then the numerator just kind of tags along for the ride. He's going to get the same stuff, all right? And now it's time to multiply it out, okay? In the numerator, I can't use a shortcut because those are not conjugates. And that's what I want you to understand. You can only use that shortcut that I just talked about when you have conjugates. So in the numerator, I have to distribute the 3, which gives me a 15. Sorry, I've switched colors. Let me try again. 15 plus 3 root 2. I have to distribute the root 2, which gives me a 5 root 2 plus the square root of 4. But now in the denominator, instead of multiplying all this stuff out, I know the middle terms are going to cancel. So I know that I'm only going to have to do the 5 times 5 and get a 25. The negative root 2 times the positive root 2 and get a minus root 4. Okay, I can cut out the rest of that only when I have conjugates. And now I continue to simplify. In the numerator, I can combine some like terms. That's an 8 root 2. The square root of 4 is a 2. Down here, the square root of 4 is a 2. I continue to simplify. Let's see, that's a 17 plus 8 root 2 all over 23. And I don't think there's anything else I can do there. So that's it. That's my answer. That's the denominator rationalized. Okay? Let's do a little bit with cube roots now. And see, this kind of takes it up a notch. The idea, once again, is I want to get rid of the radical. And see, so far, we've only been getting rid of square roots. And we do that by making sure we have a perfect square under the square root. Well, now I want to get rid of a cube root, so I want to get a perfect cube under the cube root. And so when I look at this, I want to transform the denominator into something that has a perfect cube. So when I look at a 2, I say, okay, my perfect cube numbers are like 8. Okay, that's a perfect cube. 27 is a perfect cube. 64 is a perfect cube. And so when I look at 2 and I say, okay, which of those would be easy to turn into? Well, it's easy to turn a 2 into an 8, right? And so if I want to turn that into an 8, I have to multiply it by 4, but not just 4, but the cube root of 4. And so the idea here is I want to turn that into a perfect cube. And to do that, I need to multiply the 2 by a 4. And in order to get that thing to multiply, I need something else that's on the inside. Okay? And so I multiply this out. That gives me a 2 cube root of 4 over the cube root inside times inside. That's an 8. And now I can continue to simplify. The cube root of 8 is a 2. And now look at this. The 2's cancel. I'm just left with the cube root of 4. And no, you cannot simplify the cube root of 4 any further. 4 is a perfect square, not a perfect cube. Okay? The other way you could think about this is, if we're thinking about it in terms of, the square root gets canceled out because I'm multiplying by itself. I'm squaring the thing. So think about it this way. If I multiplied by the cube root of 2, well, that's like multiplying by something by itself. That's like squaring it. If I do that one more time, see, now I have the cube root of 2 3 times here. That's like cubing it. This gives me the same result. As I multiply outside times outside, inside times inside, I get 2 cube root of 4 in the numerator. I get the cube root of 8 in the denominator. And so it's that idea of if I have a cube root, I can undo that with cubing something, so I multiply that thing by itself 3 times. And that's what I see here, right? I see that cube root of 2 3 times instead of twice, okay? If I look at the next one here, I have the cube root of 5 over 10, and what a lot of students do is they'll do this. They'll go cube root of 5 over the cube root of 10, and then they'll start looking to rationalize that denominator of 10. But remember, you should always simplify first. And if you look at this thing, you can simplify the 5 over 10 by writing it as a 1 over 2. Isn't that the same thing as 5 over 10? And now if I split this up, well, this becomes a lot easier. The cube root of 1 is actually a 1. So now I just have a cube root of 2 I need to take care of. Well, this is the same as what I did in the previous example, okay? And so the idea here, once again, is I want to turn this into a perfect cube. So I'm going to multiply by cube root of 4 over cube root of 4. That gives me the cube root of 4 over the cube root of 8. And of course, once again, the cube root of 8 is a 2. And I can't do anything else with that, okay? I can't divide that 4 and that 2 because, again, one's on the inside and one's on the outside, okay? If we look at these last two examples have I in the denominator. And I want you to understand that I falls into the same category as square roots. Remember, I is the square root of negative 1. So we're also not allowed to have i's in the denominator, okay? But think about how we kind of dealt with a square root in the denominator. If I had a root 2 down there, I'd multiply it by root 2 to get rid of it. If I had a square root of 5 down there, I'd multiply by the square root of 5 to get rid of it. So if I have an I down there, I'm going to multiply by I to get rid of it. And so the idea here is I'm going to multiply by I over I. And so what happens is this. I get 2I over I squared. And so the concept of I squared, this is the thing that we have to kind of worry about here. The I value is really the square root of negative 1. And so the idea here is that when I square that thing, the square root kind of cancels out. And so I squared is actually equal to a negative 1, all right? Which doesn't normally happen in terms of square roots, in terms of getting negative values. Normally, we talk about the idea of the absolute value being involved here. But i's are kind of special in that category. And so what we end up with is negative 2I, okay? And so really, after seeing one of these, hopefully you can remember and commit to memory that I squared, well, it's undoing the square root, which means I squared will always equal a negative 1, okay? And so moving forward, if I look at the next one, I'm going to multiply this by I over I. So that gives me, let me write it down here. That gives me a 6I over 7I squared. But once again, I squared is the same thing as a negative 1. So what I really have is 7 times a negative 1, which is just a negative 7. And I could leave it like this, but that's a little weird. I'd rather write the negative out front or stick it with the numerator. Either one would be acceptable. Sorry, this kind of didn't go out front, okay? So you could write it like this or like this, okay? But that idea of, hey, I falls into the same category as any other square root because it is technically a square root, so I have to eliminate i's from the denominator as well, okay? And if I had a binomial, I'd multiply by the conjugate. But keep in mind that I squared, when you see that thing, I squared is a negative 1, okay?